So 2957, remove adjacent almost equal characters. It's the holiday season, as you can see by this tree. So what a better gift to myself, not to you, the viewer, but to myself to make a video, because this is an honor. This is an opportunity for me to solidify my understanding of the problem. Okay, so what are we doing here? So you're given a 0-indexed string word. All right, we should be familiar with what a string is, right? A string is just a series of characters together. In one operation, you can pick any index I of word and change word I to any lowercase English letter. All right, so for example, if I had A, B, if I wanted to, I could say, you know what, I don't like this A, and I'm going to change it to a Z, for example. Maybe move that up a little bit. Okay. Return the minimum number of operations needed to remove all adjacent, almost equal characters from word. All right, so, you know, if these are adjacent and they're equal, then we'll probably have to, like, change it, right? We have to make some modifications so that we're not in a situation where, you know, we have almost equal adjacent characters. Two characters, A and B, are almost equal if A equals B or A and B are adjacent in the alphabet. Okay. So one example here. And this idea is basically, you know, they have to be more than a distance one away from each other. Okay, so if you thought about this as an alphabet, right? So if I write out the whole alphabet, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X. All right. Y and Z. Right, so this is the entire alphabet. So two characters, A and B, are almost equal if A equals B or A and B are adjacent in the alphabet, right? So what characters are adjacent to P? Well, P itself, right, is almost equal because it is itself, and O and Q, right? So if I have a P, I can't have any of these three characters next to the P, right? I can't have P itself, and I can't have O, and I can't have Q, right? So they have to be that distance away from each other. I hope that makes just a little bit of sense, okay? Now, in this example, A. So I'm going to draw it out, write it out. 3, 5 A's, 1, 2, 3, 4, 5. Well, obviously, these are all issues, right? Because for A, you can't have a B next to it or whatever comes before an A, which is nothing, right? So these A's need to be changed. And it turns out the optimal way of doing this would be to change this A and change this A, okay? And now in this example, they just change it to C. Now, it doesn't matter what you change it to, right? Changing it costs 1 point, right? Changing it costs 1 thingamajig, okay? So, you know, I could change this to a C. I could change it to a D. It can't be an A or a B, right? I can't change it to a B because that would still be an issue, but I could change it to any of these other letters, okay? So this results in 2 operations, right? I had to change 2 things to make this work, okay? Let's do another example here. So another example, we got A, B, D, D, E, Z, A, B, D, D, E, Z. All right, let's first locate the issues, right? Well, A and B are adjacent, so they can't be next to each other. All right, so this is a situation we have to handle. This B and the D, they're fine, right? Because, you know, B and D, they're more than 2 away. Like B can't be a B can't be adjacent to a B, an A, or a C. So it can be adjacent to a D, so that's fine. This D and D, of course, that's going to be an issue. Now, what's also interesting, right, is that this D and the E, that's going to be an issue, right? Because D can't be next to D, C, or E. So that's going to be another issue. I'll just make it a different color. And then E and Z are fine, right? They're on opposite sides of the alphabet. So how are we going to handle this? Well, it turns out that the answer is Y, B, D, O, E, Z. All right, Y, B, D, O, E, Z. All right, so what ended up changing? 2 things ended up changing, right? So we ended up changing this A to this Y and this D to this O. Now, of course, again, there's a lot of solutions here, right? Because this A can be anything except for A or B, right? So this could be a C, a D, an E, an F, a G, right? And the only reason I continue to reiterate that point is because it has some implications about what the solution will be, right? And this D can be anything except for, well, it's kind of confined by two sides here, right? Because this D can't be a D, so it can't be C, D, or E, but it also has an issue with this E, right? Because there's kind of like two sides to what something can be, right? Like, if I'm going to change this D to make this work, well, it can't be anything in this D space, right? And it also can't be anything in this E space. But there's still all the remainder letters, right? Because I have to kind of like, except for the edges, right? Every character has two adjacent characters it needs to think about. So it needs to look at both of them when it considers what it needs to be, right? But the thing to always remember here is, well, that's never going to be an issue because there's always going to be something that I can change the character to appease both sides, right? Because both sides, the maximum that it's going to limit is 4 characters. Or no, 6 characters, right? For example, if I had like K, I don't know, X, right? KKX here. Well, if I wanted to change this K, what am I limited by? Well, I know I have to appease both sides of this equation, right? So I can't do anything that would conflict with K, right? For this K here, and I can't do anything that would conflict with X. But I still have, how many letters in the alphabet? 26. There's still 20 options here, right? So I just know that I'm going to change this to one of the 20 options. And that's the worst case, right? They could be the same on both sides, so it just affects over here, and then I have all the options to the right, to the left, on both sides, or whatever, right? But the idea really here is, you know, in the worst case, I'll have 20 options where I can always choose. So I can always choose something. When I change a character to fix its issue, I can always pick something that's going to adhere to the rule where they can't be adjacent, right? It's going to work on both sides. That's the point I'm trying to make, okay? So I don't really even need to think what I need to change this K to, right? When I do this problem and I change characters, I don't need to think about what this gets changed to, just that it gets changed, right? Same here. When I look at this and I say, okay, I'm going to change this A and I'm going to change this D or whatever, right? I just know that I'm changing these. And whatever I change them to, that's what's going to make this work. I don't need to think about what they're actually being changed to. Okay, so I know there's 2 changes, but there's always going to be something I'm changing it to. So that kind of limits our complexity, right? It kind of makes this more manageable, because if you're trying to think about this like, okay, what am I going to change it to? That's going to add another layer of complexity to this problem. But just knowing that, well, it doesn't really matter what I change it to. I just know I have to change it, right? There's always going to be something I can change it to that will make everybody happy. So I don't need to worry about what that is. That makes this problem a little bit simpler. Okay? So that's kind of the first observation. The next thing to observe is, so I'll just say always something. Right? The next thing to observe here is, well, I don't drink soda anymore, so now I'm drinking nasty coffee. How sad. Let's think about how we can find the minimum things to change, right? Because we change something, you know, what are the implications of that, right? Which one should we change? Which one should we not change? Et cetera, et cetera, et cetera. Okay? When we look at A again, right? You might feel inclined to say, okay, which ones do I have to change? Where I look at this and I know I'd have to make a change, right? You say, oh, I look at this and I have to make a change. And I look at this, I have to make a change. Look at this, I have to make a change. But the answer is 2. Well, the answer is 2 is because every time you make a modification, you can make it work for both sides. All right, so if I make a modification here, then I can eliminate these 3 as causing problems. Right? So I don't need to worry about this character anymore because I can always make it work with A here. So then I need to worry about what comes after. Okay? So I can move here. And if I make it work here, then I can make it work for these 3. What's a better way of describing that? Okay, in a more general case, I guess if you had a bunch of characters, AA, and a bunch of characters. You have to change something in this situation, right? Because it's not going to adhere to the rule if you don't change something. That makes sense, right? You know for sure that you're going to have to make a modification here to make this work because there's two characters together that break the rules. So then it really becomes a question of which one are you going to modify, right? Are you going to modify the one to the left or are you going to modify the one to the right, and what are the implications, okay? Well, let's assume that we've already combed through all of this to determine that there's no issues, okay? So we went from left to right and we went through and we started changing characters as we found them using some approach that works. And we got to this point. Well, at this point, I'm going to say, okay, I have an issue. I have an A here and I have an A here. One of these needs to change in order for this to work. But which one should I change? Well, I guess the first thing to think about is, well, if I modify this one, what are the implications? Well, if I modify this one, or I modify this one, what are the implications here? Well, if I change the first A, I can make it work with this side. I can make it work with both sides. How do I explain this, right? Let's say, just for the sake of argument, right? Let's look at it like this. Let's put another A here and put this down the line. Okay, let's say with 3A, so you can see this point. I apologize. It's one of those problems where it's very conceptual. All right. There's also a dynamic programming solution, but that's much harder to understand, and it's actually less efficient. Sort of. Depends how you want to look at it. But we have these 3 A's, right? If I change this A, I can make it work. Right? But then I'd still have these 2 A's as issues. It's best to change the A in the middle because I can make both of these guys happy at the same time if I modify the A in the middle. Okay, so if I have 2 things that are causing an issue, I might as well change the latter one because changing the latter one will also fix any potential issues in the future. Right? If I modify this one, this only results in the resolution of these 2. But if I modify the top one, I get the resolution of all 3. So what that basically means is when I look through this problem, the optimal way of always doing it, right, is to be looking through and saying, well, when I get here, I might as well modify this because it'll fix these 3 problems, right? If I change it here, then that's only going to modify these 2. So I'm maximizing what I can fix with one change. So that's kind of a greedy approach here, right? So kind of greedily try to maximize the modifications you can make when you have to make a modification, right? So go through your system when you have things that don't meet the conditions, right? Where they're almost equal, then make a modification. Which one should you modify? Modify the one that's going to cause the maximum amount of change. Terrible description today. I do apologize. I'm not feeling super well, but let's go ahead and implement this. All right. So what we'll do is we'll keep track of how many modifications we made, and at the end we'll return the number of modifications that we made. We'll never modify the first thing, right? We'll never modify the first character because you should always, if there's 3, right, like we had 3 characters before, we never modify the first one because modifying the second one could help us with the subsequent character, but modifying the first one won't. Right, if you have AAA like this, modifying this doesn't help, right? Modifying this helps. Modifying this works, but modifying this one is better. So might as well start by modifying here. Okay. Let's go for I in range 1 to length of word. And we'll basically say is, well, let's figure out if they're almost equal. So if almost equal, what does it mean if they're almost equal? The difference between them is less than 2, right? The difference between them in the alphabet. So if I said the absolute difference between the word at the current character minus the word at the previous character is less than 2, then they're almost equal, so we might have to do something, right? Now, this is a character, so we want to figure out the order of these characters. So the order of it will return its kind of placement, and the difference of the order will return the distance between the 2 letters, right? So the order of A is, 90, The order of B is 91, so then 90 minus 91, negative 1. Absolute of that is 1, so 1 is less than 2. Yes, that means they're next to each other. All right, and then what we'll do is we'll say, okay, now they're almost equal. So if they're almost equal, we're gonna have to add 1 to our score. Now this is gonna fail because it doesn't capture the idea of resolution. All right, this says 4 instead of 2. Why does this say 4 instead of 2? Well, what happens here, right, is we have n 2, 3, 4, 5. We start here at 1, right? We modify this. That's going to give us, I'm just going to put an X, not the letter X, but an X to signify that we're, making a modification here. And then when we get here, we could, I guess technically, so what I'll do is I'll modify word, because what I'm going to end up doing is when I change it, I can modify it to anything that will fix the problem. So this is a string, so I don't want to modify a string in place, right? But basically what I'm going to do is I'm going to change this current letter to a letter that appeases both sides, right? Because remember, in the worst case, there's still 20 letters I can choose from that will make my left neighbor happy and my right neighbor happy, right? So I'm going to change it to something here. Okay, so then when this A, because what's happening in the code right now is even though we've noted that we're making the modification here, right? We've added 1 here. That's not being noticed when it gets here. It still compares A to A. It doesn't realize that we made this modification, so then it says 2, right? And then it says, oh, we make modification. That's how you get 4 here, right? Versus what really needs to happen is, you get here, you say, I'm going to make a modification. I'm going to change this to an X that appeases both of these. So then when I get here, this thing's like, oh, am I good to my left? Yeah, I'm good. Move over. Am I good to my left? No, I'm not, so I'll change this to an X. Right? And then I get over here and I say, okay, am I good to my left? Yeah, I'm good. And then you get 2. So basically, so we could change the character to something, but that's going to actually affect the runtime a little bit and the space complexity because strings are immutable, right? I don't know if they're probably immutable in Python. I'm just going to assume that they are, right? So if the string's immutable and then you make a modification in place, right, it's going to cause issues. So instead, what we'll do is we'll say, well, if we modified the previous one, then we don't need to change the current one, right? When we go through here and we walk through, what I can instead say is I'll keep track of what I modified, right? So if I have to modify this, I'll have my modified value be true, like my modified flag. So when I'm here, I'd say, okay, even though the previous thing's an A, since I'm previously modified, I know that previous thing got changed. So modified is false now and continue on through. So if I say, and we haven't modified the previous thing, I'll just call that M, or modified, I don't know, and not modified. So when we modify something, we set it to true. Otherwise, we get to this case, and that means we didn't modify anything, so we say modified equals false. And of course, we should define modified up here as false. So but basically what I'm saying is, all right, do I have an issue with the previous character and I didn't modify the previous character? Because if I did modify the previous character, I would set it to something that would appease me. Now, whatever that is, there's 20 options in the worst case that I could use. Okay. Hopefully that makes a little bit of sense. Boom. Why is that? What have I done wrong here, guys? 0. It should definitely not be 0. For I in range 1 to length of word. Oh, I didn't. Oopsies. This is less than 2 and not modified. Surprised it even let me run that. Yeah, these are separate conditions, right? If this is less than 2, so if they're neighbors or almost equal, and it hasn't been modified. If it has been modified, then that means that the previous thing we modified could be changed to something to make this work. Why is that so slow? Wow, that's crazy. All right, so what is the space and... Guys, why is it so slow? So that's why, now it's 59. So don't always trust this, especially with solutions that are so quick and all of them are going to be so close. You're going to be all over the board. I could keep doing this until I get, the number I want to see. Okay. So let's say n is the length of word. All right. Let's say time And space. So for space is pretty simple. Notice I only make these two variables and then I update them accordingly. I don't create any other variables. So for space, that's constant space. Now for time, I have to look at all the letters in the word. I do a constant check, constant operation, constant check, constant operation, and then I return it. So I do n things, and for all n things, I do something constant. So I do n constant things. It's big O of n. All right, everybody. I hope you have a beautiful rest of your day. Bye-bye.